And now I'm going to solve for the other side, which is what Shu Shen did. And basically, I have 20 sine of 5x minus 17 cosine of 5x. The 5x doesn't really matter in this case because we already know it, but I still used it in my guess, so to speak. So I said that my right side should, in theory, be some multiple of a sine kt plus b cosine kt. And I realized like halfway through that I accidentally swapped variables. So t and x are the same thing. But basically, I take the first derivative of that, but that's not in our formula, so we don't really care. Second derivative, third derivative, and fourth derivative. And if you'll notice, the fourth derivative is the same as the original function, except with k to the 4. And the second derivative is basically the first function, but negative. So, and of course we know k is 5 because there's nothing you can do to a derivative to really get rid of this 5. So plugging that in, we get, we plug this in here, and we plug this one in here, and we keep the right side as it was in the original function. So that's what I did. I plugged in. We know k is 5 again, so I basically just substituted in 5. I also split the sines and the cosines up because we can equate the sines of both sides and the cosines of both sides. And in this case, because I have negative y double prime, which is basically the original function but with k squared, and y quadruple prime, which is the same function but k to the 4th, I basically have two functions or two equations independent of each other, one in terms of a, one in terms of b. I basically just solve for a and b, and then I plug it into the general equation. So we have the one from before, which is the left side solution, and then the one here, which is using this form right here. This
A particular solution.
right. So here's our particular solution for the right side with a and b plugged in.
Great. Anyone has any question? Okay.
Thank
you, Ron. Christian. Christian has his own version of 11.4.
Professor, you can hear me?
Yeah.
Okay, sorry. My mic was off. A mistake. Okay, so my question is along the lines of Shu Shan, I believe. And yeah, so it's like the only changes that's there is the fact that I just changed up the coefficient for right here, my f of x. We assume the right side to be f of x. So for f of x right here, the coefficient is -6 and -28 right here, and then -4. Other than that, it's the same question as question 4 for chapter 11. So let me go right into it. So the question is, find the particular solution yp of a given equation. And then we're going to say, okay, what are we dealing with? And if you look at the equation, it's a non-homogeneous differential equation due to our differential equation being equal to a non-zero. And since this non-zero is -6 cosine x, we're going to use the method of undetermined coefficients to find or what it said in the notes, sort of guess in what form the particular solution should be. And the general form that it should be in is yp is equal to a cosine x plus b sine x. And when we have this particular solution, what we're going to do is derive it twice. And in doing so, we're going to be able to substitute our values, our yp values that we derived, into the differential equation that we have above right here. And like the yp double prime corresponds to y double prime, and then so on and then so forth. And so we're going to substitute in our values, and then when we substitute in our values, what we're going to do is just use the distributive property. And then after we distribute for our equation, is going to simplify, is going to help us simplify our equation. And as we go along and distribute and combine our like terms that have cos x. So we're going to combine cos x from this side and right here, sine x from this side, and sine x right here. And then we're going to bring that down. Since we have everything aligned and right next to each other, all we have to do is factor out our constants for the left side of the equation. And for the right side of the equation, I did a little trick in which that it doesn't have a sine x, but we can put in a sine x by implying that it's still going to be equal to this side of the equation. It's just that we have a zero coefficient multiplied by sine x. And in doing this trick, we have our coefficients corresponding to each other from the left side of our equation and the right side of our equation, which is this coefficient right here, this coefficient right here, both corresponding with one another, and then this coefficient corresponding to this zero coefficient. And yeah, and you could just look at it as, okay, they both have sine, both of their coefficients are going to correspond with one another. And in doing so, now we can use our found coefficients to create a system of linear equations. And this system of linear equations is denoted right here. And with this system, what we're going to do is just use plain old algebra. We do this 1,000 times to solve for B and A. And we're going to do it with substitution for both instances. Once we this is more algebra on the right side, 6 right here. We just one equation, which is going to be the one equaling to 0. Do some algebra, isolate the a, take that a, substitute it into our equation up here that has -6, and then we have our value for b because it's all in terms of b. And then the easy part comes along when you have your value for b, just substitute it into any one of those equations, and then you could just find your a. Substitute your b, get your a. Okay, after I did that, now we have our constants. We have our a and we have our b. And so now we can plug in our found coefficients into the general form of our particular solution, which we found over here to the left. And so once we have our general form and take a knowledge of that, acknowledge that, we're just going to substitute in our a and b values. And so the answer is going to be yp is equal to 174 over 857 cosine x plus 24 over 857 sine x. And it can be simplified to 1 over 857 times 174 cosine x plus 74 sine x. So that's my answer.
Okay. Okay. Anyone has any questions?
Okay.
All right. Thank you, Christian. Jun-Yi, you have your own version now? Yes. Okay, go ahead, Jun-Yi.
Yeah. Okay. So Professor, I just changed the right-hand side numbers instead, and I recalculate all the things again. So
is this 5 prime, I guess?
Yeah. Oh, yeah. Sorry. This would be like y double prime minus y prime minus 2y equals to 2e to the 3x. So it's the same as similar question with them. So just find a particular solution. So I take it out like f of x equal to the 2e 3x and take the derivative like y of p. So it's and the second derivative also like y prime of p equals to 3aex and y double prime is 9a e to the x. Then I plug it in to the equations and I got 4a e to the 3x equal to the 2e 3x. Then I solve out, like I found out a is equal to the 1/2. So the particular solution to this equation is y sub p equal to 1/2 e to the 3x. Well, like I do the extra step, like I also found a y sub c, which is the homogeneous equation. I do the characteristic equations and I got a c1 e to the negative x plus c2 e to the 2x. And the like general solution for this equation is capital Y equal to c1 e to the negative x plus c2 e to the 2x plus 1/2 e to the 3x.
All right.
Okay, thank you.
Anyone has any question? Okay. Let's see. Oh, Yaprak, you want to present 10.3 modified? Go ahead.
Yeah.
Then last one is Katerina.
So I basically changed the given values MC, K, X naught, and M naught. So first I checked the determinant, like with the given C, K, and M values, and I realized that it's greater than 0, so it means the motion is overdamped, and it also implies that we'll have like 2 real negative roots after calculating the characteristic equation. And indeed I see that it's like it's -3 and -5 for the roots of the characteristic equation. And then for the position function, we need to use this template function.
Hold on.
Yeah.
Hold on.
Sorry for this. Let me erase it.
You're factoring. 3 times 5 is 15. Maybe you want to change your numbers. You want to switch your C and K.
Oh yeah, my bad. I'm sorry. I didn't realize that.
Right. If you switch these two, right, you still get this.
Yeah.
Oh, hold on. More now this is less than 0 if you switch those two.
Maybe I should do this presentation later, because yeah, I messed up. I
Yeah,
think.
do it later. Right, those two.
Yeah,
right.
I'm sorry.
That's okay. That's all right. Yeah, fix it, then.
Okay.
Okay. Davy, you want to present number 5 from 10? Okay, Davy, 5. Let me make you present it. Let's see, anyone else? Oh, Katerina. Katerina, are you?
Yes, I'm ready.
Oh, okay. So maybe after David, okay?
Okay, yeah, no problem.
Okay, because he says chapter 10. David, are you ready? Or you want Katerina go first?
Can she go first? For some reason, it's not sharing.
Oh, okay. Okay, Katerina, you can go.
Okay, back to me. Okay.
Sorry.
Give me a second, please. Let me know if you can see it, please.
Okay, yes.
Yes, okay. So I needed to find a particular solution for this example, y double prime plus 4y prime plus 13y equals 20 e to the power of negative x. So I set my fx equals 20 to the power e to the power of negative ex, and I chose this. It was a guess, so yp was equals to a e to the power of negative x. Then the second derivative of that, so y prime of p equals to y negative a e to the power of negative ex, and y double prime p is just it's the same as yp, which is a e to the power of negative x, and then yp would be equal to 13y, y prime p would be equal to 4y prime, and then y double prime p would be equal to y double prime. So I plug that in, and we would get this equation. I distributed the 4 right here, and I distributed 13 here, which would give us this a e to the power of negative x plus 4 minus a e to the power of negative x plus 13a e to the power of negative x equals to 20 e to the power of negative x. And then I just combined the like terms. So I placed all the a's together, and I factor out the e to the power of negative x. And then a plus 1a plus 13a minus 4a would be just 10a, with the factor out of e to the power of negative x equals to 20 e to the power of negative x. And I just divided both sides by 10 e to the power of negative x, which would give us a would equal to 2. And then we would just substitute this a equals to 2 to our yp, and this would take a form of yp equals to 2 e to the power of negative x.
That's it.
Yes.
Okay. Okay.
Thank you.
Thank you. And David, right? And anybody else?
Okay, so this is from last class. It's about vibrating springs. It's number 5. I don't believe anyone presented it last time. So in this case, I calculate c squared minus 4km to identify what kind of system we're operating under, and it turns out to be less than 0. So it's underdamped, and then I put it into this equation that is given for the underdamped and for all of the situations. And then I solve for my value of r. That skip step over there is just by allowing x the double prime equal e to the rx, and then factoring it out, and then dividing it under, and then we're left with that polynomial, and we can use the equation to solve for the real plus imaginary to get our roots. And then we can use one of the theorem that we learned in the class before to put that into the equation, and just have the real e to the negative 5t a cosine 5t, the 5's inside of the sinusoidal functions. Those are the i's, the imaginary part. And then we can take the derivative and obtain a function for time of velocity. And then we can solve for these things because we're given these parameters at x of 0. The position is 0, and at v of 0, the position is 10. We can kind of plug those in, and then we can solve for our constants. And so we need to find c, and in this case, there is a problem because a actually ends up being equal to 0, and we need to put b over a into our arctan, because the alpha which we need is equal to arctan times b over a. And so in this case, I believe we do not add any alpha, because basically you can't add any multiple of pi that will get it into acceptable range, because it starts on the edge of what's acceptable, because it has to be between pi over 2 and negative pi over 2, and it can't be on top of pi of 2 or negative pi over 2. And if you add pi, it's going to be outside of acceptable range. And if you add 2 pi, it's still going to be out of acceptable range. And so you kind of just leave it out. And so that's the x of t. For the case where c equals 0, where it's undamped, not underdamped, you go through the same process again. You find your u of t, you take the derivative. The same thing happens again. You end up with an arctan of constant radical 2 over 0, and then you put it in the equation, you leave out alpha because it's undefined, and yeah, that's the answer for u of t.
All right. Anyone has any question? All right, so some of us already presented work from this lecture 11 on non-homogeneous equations. So we're going to talk about a couple of methods of undetermined coefficients and a variation of parameters. So let's remember that we call this particular solution. Right? This y with a footnote p means a particular solution for a non-homogeneous equation. Right? The non-homogeneous equation is like this. We have nth level a derivative n minus 1 up to a second level derivative, first level derivative, then the function itself, then equals to some function of x. Right? We have the equation in this form. So the general solution, we use a complementary, so a particular solution plus the rest of the solutions, which we call complementary solutions. The complementary solution is a general solution for the, remember, associated homogeneous equation, which means we make a special case for f of x, where f of x to be 0, and then we call it associated homogeneous equation. So the complementary solution is a solution for such associated homogeneous equation. That's from previous. So now our new method, undetermined coefficients, is a way of guessing. So I already see some presentations, a guessing solution. So how do we guess? We guess a solution based on this f of x. Okay, based on this f of x, so with different kinds of coefficients of the variables. So the method of undetermined coefficients is a way of guessing a form of a particular solution. So this is y with footnote p, a particular solution based on f of x. So if f of x is simple enough, we might be able to do that. For example, if f of x is a polynomial degree m, we have seen degree 1, and we have seen some sine cosine from the presentation. So we might guess the particular solution is also a polynomial of degree m, right? If f of x is related with sine x, cosine x, and we may guess a particular solution is with a cosine, sine, with some different kinds of coefficients. Right, so particular solution. So this is a polynomial of degree m. Then we could plug a particular solution into the non-homogeneous equation and try to solve for the coefficients. Right? Like in the presentation, we see they did this. So similarly, for if f of x is related with cosine and sine, we also, guess the same. Let's see this example. This example, we have a y double prime minus 5y prime plus 6y equals to a linear equation, right? A linear function, which is a polynomial of degree 1. So let's guess a particular solution to be a linear function, right? With different coefficients, ax plus b. Then we take a derivative of this particular solution, first level, first derivative and second derivative. Then we'll plug back in to the original differential equation and try to solve for a and b, right? Because f of x gives this constant, right? The coefficient before x and the constant term. So we simplify this. Right? Once we plug in, we simplify. Then we match up with like terms. So see this x term on the left-hand side, x term on the right-hand side. Because this is equation, so their coefficients have to equal each other. So that tells us 6a equals 12. And for the constant term, 6b minus 5a equals to 8. So a equals to 2, we plug in, we get b equals to 3. So we get a particular solution to be like the f of x, but with different coefficients of x and constant term. So a particular solution is 2x plus 3, comparing to f of x. So f of x is 12x plus 8. So that's this method. Okay, that's this method called undetermined coefficients. Undetermined coefficients to solve a non-homogeneous equations as this by inherit the idea from previously. We split the solution of such differential equation into two parts, a particular solution plus the rest of it, called complementary solutions. The complementary solution is a general solution for the associated homogeneous equation. So this is an example. All right. F of x is such, so just assume a particular solution as a linear, because this is a polynomial degree 1. We assume a particular solution to be a polynomial degree 1 or linear function. All right. Find the first derivative, second derivative, plug back into the equation. Then try to solve for a and b. In the end, we did get a and b. So we plug back into the particular solution to get 2x plus 3. Well, to solve for the complementary solutions, so we put the homogeneous, no, we make an associated homogeneous equation, which we let the right-hand side of the equation equals 0. So basically, we let f of x to be 0. So we make this to be 0 to solve for the complementary solutions. Then, out of this, we have this characteristic equation. And we can factor this. So we have two solutions. R has to be 2 or 3. So the complementary solution is C1 e to the 2x, right, plus C2 e to the 3x. So put all this together. So the solution, a typical general solution to the homogeneous equation, to the non-homogeneous equation is such, is a sum of a particular solution plus its complementary solution. So this is a complementary solution and plus a particular solution. Anyone has any question? All right, let's see example 2. F of x is 2 sine t, so that involves cosine sine. So we just guess a particular solution to be a sine t plus b cosine t. Then first level derivative, second level derivative, plug back in to the non-homogeneous differential equation. Match up with the left-hand side and the right-hand side, sine, cosine. Right, the coefficient of sine on the right-hand side is 2. So on the left-hand side, they have to agree with each other. And this one, the right-hand side doesn't have a cosine, that means 0. So we have those system of two equations. We solve for a and b. get A equals negative 5 over 17, B equals 3 over 17. Then we plug back into the particular solution. So A is negative 5 over 17, and B is 3 over 17. So have this as a particular solution. Then we try to solve for the complementary solution. So this is YP, we try to solve for YC. Well, YC is a solution, a general solution to this associated homogeneous equation. So characteristic equation is such factor. So we get two solutions, 4 and negative 1. So the complementary solution is a C1 e to the negative 1t plus C2 e to the 4t. Right? So put them together. For the original non-homogeneous differential equation, is a general solution is a particular solution as such plus its complementary solution. Any questions? Two parts, right? So we use undetermined coefficients to make a guess. You know, the guess is similar to the f of x. Then just with different coefficients. Then solve for the coefficients. That would be a particular solution. Then the complementary solution comes from making an associated homogeneous solution by using its characteristic equations. Okay, let's see this example. Well, f of x is 3e to the 2x. So we'll do the same thing. So we'll guess a particular solution to be a times e to the 2x. So first derivative, second derivative, plug back into the differential equation. Solve for a and b, a equals negative half. Or just a, there's no b, right? Just a, just one term. Just 3e to the 2x. So a particular solution is negative half e to the 2x. For this one, we just want to find a particular solution to this. Let's see, find a particular solution to this one. Similar, right? Guess a particular solution to be a e to the 3x. First derivative, second derivative. Then put it back into the differential equation. Solve for a. Oh, in this case, we see what happens. We see what happens. This thing we get, so when we do this, we get 3e to the 2x. And this will never be 0. So no matter what a we choose, right? You see, this is e to the 3x, e to the 3x, e to the, so this is e to the 2x. So that means, oh, this side is 0. So 0 equals to 3e to the 2x. So it doesn't matter what a is, this won't work. So no solution for this, no solution for such differential equations. Any questions? Let's see, let's try something else. Shuxian, question?
Where your E2x came from? Could you come back? You said 3E2x. Maybe you make a mistake, right? That's a 3x.
Oh,
it's not 2x.
e to the 3x, right? E to the 3x. E to the 3x. E to the 3x. Sorry, that's a typo. That's a typo. Right? E to the 3x. So that way it won't work. So let's see, what do we do? So let's try something else. We add x into it. So we guess a particular solution to be ax e to the 3x. So we multiply by x. Then we differentiate again. We plug back in. Now, oh, sorry, all those are type O's. Sorry, because sometimes copy paste, sometimes the copy paste forgot to change. Sorry. So all those are e to the 3x. In this case, it works. So we did get a equals to half. So we did get a particular solution to be half x e to the 3x. Yes, David?
Can this adding of an x be used with other methods? For example, like the first method, can I just add it into both terms and make like y a particular solution equal ax squared plus bx?
Which one?
Like, the first example where it's on page 2, where it has yp equal ax plus b. Would it be possible just to make it ax squared plus bx? Or like, can you do that for any of them?
Well, why do we want to do that? Because this you're talking about this one, right?
Yes.
Yeah. What just in case we, if we do not get a solution? Yes. Yeah. You're good thinking. Yes.
So if it's like 12x squared, or something like that on the right side.
Yeah, you can try that. Yes. If this way doesn't give you a particular solution, yeah, you may try something else. You may try go with 1 degree higher.
Thank you.
Good thinking. Yeah. Yeah. So why this one is this? Why this one worked? Okay. Why this one doesn't work and the other one worked? Because sometimes we did get double root, right? When we get double root, the first coefficient of a something could be 0, and the c1 something, c1 could be 0, c2 is not. That's for this case. Let's see. You see, we could think c1 is 0 and c2 equals to half. So we did get a particular solution to be half x e to the 3x. Sorry for those typos. Okay. So let's see. We have these two rules. If no term appearing in f of x or in any of these derivatives satisfy the related homogeneous equation, then take a particular solution to be a linear combination of all linearly independent such terms and their derivatives. Then find the coefficients by substituting a particular solution into the non-homogeneous equation. So the previous example give us this, right? Characteristic equations, we get 3 and -3. So a complementary solution would be this. And we guessed a e to 3x couldn't work since it's part of the solution to the homogeneous equation. That's from the previous one. So let's see this example. So we have such differential equation, right? We have t squared plus 3 sine t. We have polynomial of degree 2, and I have sine. And this one with two initial conditions. Well, this is the highest one is the second derivative. So first, let's get characteristic equation. Right? We're trying to solve for the complementary solution. Because this one, because we have t squared polynomial, but we have sine t, so it's a combination. So what do? And from the undetermined coefficients, we learned either we make a polynomial or we make a sine cosine. So with this combination, what do? So we try to solve for the complementary solutions. So what do? We make associated a homogeneous equation, which means we make this to be 0. Then its characteristic equation is such, and this is factorable. So we have 2 r's, -½ and -1. So complementary solution is this. C1 e to the negative t plus C2 e to the negative half t. So how do we find a particular solution? We make polynomial degree 2, then plus sine and cosine. How many variables we have? We have A, B, C, D, E. We have 5 variables because this is polynomial degree 2. Right? So we take a derivative, we differentiate once, we differentiate twice, so get this. We substitute into the original differential equation. We get a lot of terms. Then we compare the both sides of the equation. So we say A equals to 1, because the coefficient of t squared equals 1 on the right-hand side. And for t term, there's no t term on the right-hand side. That means 6a plus b equals 0. Then no constant term. That means this constant equals 0. For sine, that's 3. That means negative d minus 3e. That's 3. There's no cosine. That means 3d minus e. That's 0. So we did get 5 equations and the 5 variables. So we can solve for the 5 variables. So we get b equals negative 6, a equals 1, c equals 14, e equals negative 9 over 10, d equals negative 3 over 10. Then we just plug everything back into the particular solution, which we get t squared minus 6t plus 14 minus 3 over 10 sine t minus 9 over 10 cosine t. So to get a general solution for the non-homogeneous solution, and we just put complementary solution and a particular solution together. So we'll get this. Get this. All right, we are given initial conditions. We're given y of 0 equals such, y prime of 0 equals such to initial conditions. So we plug in for t at 0. So we get C1 plus C2 equals 1. We plug in 0 for y prime t. Then we get this equation. So solve the system of these two equations. We get C1 equals negative 3, C2 equals 4. So we do get a particular solution, a unique solution for the given two initial conditions. Anyone has any question? All right, let's see this one. We have x cosine x e to the 2x. And this is the third level of derivatives. Okay, so first we want to solve for the complementary solution, all right, yc. So which means we make this one to be 0. We form a characteristic equation. Factor this way, so get a 0 and a plus minus 2i, two complex roots. So we have a complementary solution as, well, for 0, we get a C1 e to the 0 x, which is just C1. C2 cosine 2x plus C3 sine 2x. Okay. Because the real part is 0. So e to the 0 just 1. So we just get C2 cosine 2x, C3 sine 2x. Okay. And look at the function. So this is of our f of x. So f of x is this. And its derivative involves, so this is product involves x sine x, x cosine x, sine x, right? Cosine x, or itself and e to the 2x. So because it has all those terms, so we just make a brief guess saying, okay, a particular solution has to include all those terms with some different coefficients. So ax sine x plus bx cosine x plus c sine x plus d cosine x plus ex e to the 2x plus f e to the 2x. Okay, no example for this. Okay, the second rule. So if we have this f of x can be written as a sum of, some function of x e to the rx cosine kx, or some function of x e to the rx sine kx. Right? And this one is a polynomial of degree m. Polynomial of degree m. So then what do? We take a particular solution as such as x raised by s. So where is s? S is the smallest non-negative integer such that no term in the particular solution duplicates a term in the complementary solution. Then has this polynomial of degree m, e to the rx cosine kx, then also x raised by s, this e to a polynomial of degree m, e to the rx sine kx. All right, let's see this example. We want to find the form, you see, because it gets too complicated. The form of y, a particular solution, for this non-homogeneous differential equation. First, we're treating this f of x to be 0, so we form a characteristic equation, and that is r minus 1 cubed equals 0. So r equals 1. So in this case, because this is the multiplicity is 3, so when the multiplicity is 3, we have a constant term, we have a linear term, we have a quadratic term. Then e to the x, because r equals 1, so e to the 1x. So this is a complementary solution to the associated non-homogeneous equation. Associated homogeneous equation by treating this to be 0. So we may guess a particular solution has a form include all this, right? X e to the x term and e to the x term with some different coefficient. So a times e to the x and the bx e to the x. But this particular solution is a part of the complementary solution, right? Because you see e to the x, e to the x, x e to the x. So if we plug in a particular solution as this into the non-homogeneous equation, the left-hand side would be 0. So we wouldn't be able to find AB. So by root 2, we have to multiply this by x raised by s, x raised by 3 in this case. So neither term is part of this. So the smallest non-negative integer that will work is, for this case, is s equals 3, because we do have x squared in here. We have x squared, we have x raised by 1. So the smallest one works for this. So the particular solution won't be part of the complementary solution. Starts with cube, x cubed. So what do? We multiply x cubed. Remember, that's x raised by s. So multiply by x cubed. So a particular solution is this: x cubed times a e to the x plus b x e to the x. Anyone has any questions? So this is by this rule. So it just multiply x raised by s. And this s has to be the smallest number works for the particular solution not to be part of the complementary solutions. For this example, because we see x raised by 1, x squared e to the x, so we multiply by x cubed. Multiply by x cubed. So it will be different than this. So it won't be part of the complementary solutions. Okay, let's see an example. So we want to find a particular solution for this. Third level derivative, second level derivative, and f of x is such. Polynomial degree 2 plus e to the x. Okay, we want to find a complementary solution first. So thinking this one to be 0, form a characteristic equation and factor out, we get a double root for 0 and a root -1. So the complementary solution would be c1 e to the 0, which is 1, c2 x e to the 0, which is 1. So we have c1 plus c2 x, then plus a c3 e to the x. So a complementary solution. So our first guess for this particular solution would be something similar to this, but with different numbers. So it will be a e to the x plus b plus cx plus dx squared. So this is, however, a e to the x does not duplicate any term of this, right? You see, we have c1 constant term, c2x, c3 e to the negative x. Only those two. But here we have x squared term, we have e to the x, especially e to the x term, will not duplicate any of this. So this is our complementary solution. So we need to multiply this part by x s. In this case, s equals 2. Why? Because you see, we only have x raised by first power. X raised by first power. So in this case, s equals 2, which is multiplied by x squared. So a particular solution would be in this case, then we'll take a derivative, we take a derivative again, then we differentiate again to get this. So substitute back into the original equation, then match up with the left-hand side and the right-hand side, the coefficients. 2a equals 4, a equals 2, and this, and d equals 1. So solve this system of equations. We get 2, 3, 2, 1. So plug back into the particular solution. We get this. E to the x, 2e to the x, 3x squared, 2x cubed, plus x raised by 4. So our general solution would be the two-part. So the complementary solution and a particular solution. Any questions? Let's see one more example. F of x, in this case, we have e to the negative 2x and sine 3x. Again, we treat this one to be 0. We form a characteristic equation. We solve for the equation. We get two complex roots. Then the complementary solution will be e to the negative 2x, the real part, e to the negative 2x, real part, multiplied by c1 cosine 3x. 3 comes from this complex number, plus c2 sine 3x. So a particular solution we maybe guess at as e to the negative 2x, right? Oh, okay. I was thinking to put an a here. Well, it's the same thing we put over here because we have a sine 3x here. So a cosine 3x plus b sine 3x. To eliminate the duplications, we multiply by x, right? Because in the complementary, what do we have? We only have cosine 3 or sine 3. So we don't want to duplicate with this, so we multiply by x. So we make a particular solution to be e to the negative 2x, a times x cosine 3x, b times x times sine 3x. Any questions? Yes, Sushan.
I still confused, and then the y have something multiplied by x, y multiplied by x squared, but it depends on, so
Okay. So
I get confused this.
you see here we're solving for complementary solutions first. When we do that, if we go back to get the particular solution becomes a part of the complementary solution.
Huh?
Let's go to, here. Let's go from the very beginning. Or maybe we use example. That's too complicated. Okay, let's see this one, right? So first we treated this one to be 0. We form a characteristic equation. We solve for it. Then we get a complementary solution as such. C1 e to the x, C2x e to the x, C3x squared e to the x, right? No problem for this part.
Yes, no problem.
Okay, no problem with this part. Now, remember how do we guess when we do the undetermined coefficients? We guess a particular solution, right? We guess a particular solution to be similar to f of x. In this case, we still have 2x minus 3 e to the x. So basically, we have 2x e to the x minus 3 e to the x. So we do the same. We guess a particular solution to be a e to the x plus bx e to the x. No problem, right?
No.
Now, comparing those two. Compare this particular solution with this complementary solution. What do you see? Do you see some terms are the same?
Oh, the yp is a plus b, a
Right.
plus bx, like a fractal ex, like yp. Only two coefficient only a plus bx. Here has
right. You see C1. You see C1 e to the x.
Yeah.
A e to the x, right? And the C2x e to the x, and the bx e to the x.
Oh, we're missing C3x squared ex.
No, we don't want those two to be the same because a particular solution Then this is the rest of the solution called complementary solutions. But you see those two have duplicates, something overlapping.
Oh,
You
okay.
see this a e to the x overlap with the c1 e to the x.
Yeah.
Ex overlapping with the c2x e to the x. And we don't
Okay,
want
got
that.
you.
Yeah,
Alright.
that becomes, okay. So that's why we have to multiply by x raised by s has to be higher than this.
Oh, okay. All right.
Okay.
Okay, got you. Yeah.
Okay, you
Okay.
see here, this is a polynomial of 2. So what do? We multiply by x cubed. If inside the polynomial of 3, we multiply by x raised by 4, so on and so forth.
Okay.
Just
All
to
right.
make sure, okay, just to make sure the particular solution is not part of the complementary solution.
All right. Okay. Thank you.
You're welcome. Okay, any other questions? Okay, last part. Variation of parameters. For an equation like this, cotangent x, we cannot use undetermined coefficients because f of x equals cotangent x has infinitely many linearly independent derivatives. So variation of parameters is a method in principle can be used to solve any non-homogeneous linear differential equation of such form. Okay. Polynomial of n minus 1, degree n minus 1, so on and so forth. However, the method can give rise to integrals that could be difficult to evaluate. Let's see this one. We have y double prime plus polynomial of x, y prime plus polynomial of x, y equals f of x, with a complementary solution to be c1, y1 of x, c2, y2 of x. We want to find two functions, u1x, u2x, such that a particular solution would be u1x, y1x, plus u2x, y2x. So we have to find u1, u2, so that the particular solution satisfies such equation. This is the original differential equation. So the first condition, right, for the particular solution, and the second condition is for u1, u2. We have this, right? This. So when we differentiate this, we get this. We apply product rule to get this. So the second condition becomes this. And the double prime of those two don't appear when we take y double prime. So we have the first derivative, we get this. The second derivative, we get this. Okay. If you have little problem to see this, calculate it yourself, right? So both y1 and y2 satisfy the homogeneous equation when we make the f of x to be 0. And then we get y double prime to be this, right, related with p and q. The y1 double prime, y2 double prime. Then the particular solution double prime will have this, original equation is this. So get those two equations. Now Wronski. Solving for this U1 prime, U2 prime. Get this kind of relationship. So the particular solution is written this way. So we have to integrate this guy. We have to integrate this guy. So we get such as a particular solution. Okay, this is all dry, and let's see an example. Okay, we want to find a particular solution for this. Y double prime plus y equals cotangent x. So we want to find complementary solution, C1y1 plus C2y2. So the characteristic equation formed to be this. So get 2 plus minus I. Then the complementary solution will be C1 cosine x plus C2 sine x. Right. So what is C? So C1 is this. What is y1? Y1 is cosine x. What is y2? Y2 is sine x. Right. Compare with this. So y1 prime is negative sine. Y2 prime is cosine. Now let's calculate Wronski of y1, y2. This is cosine sine, negative sine, cosine. Cosine times cosine, cosine square minus negative sine square, that become plus. Cos square plus sine square, identity, that's 1. So Wronski, so we get 1 over, right? Think this way, 1 over 1, because Wronski is just 1. Just negative 2 f of x. Right? Then we integrate it, so negative y1. Integrate this y2 f of x. Well, Wronski just 1. Right? What's y2? Y2 is sine x. F of x is cotangent x. Okay, that's f of x, cotangent x. So y2 is sine x. F of x, cotangent x. Then Wronski just 1. So integrate this term. And the second term is y1, f of x. Y1 is cosine x times cotangent x. Wronski again is 1. So I have this dx. Well, cotangent is cosine over sine. So that's simplified to be cosine x. Cotangent is cosine over sine. So I have cos square over sine. Now integrate this. Integrate this one is easy. It's just negative sine. Integrate this one. We think we could, okay. We need to change a little bit, right? We need to change a little bit then to be able to integrate. Cosine change to be 1 minus sine square. Cosine square is 1 minus sine square. Then we have 1 over sine, which is a cosecant of negative sine square over sine, which is a negative sine. So we split into 2. A negative sine, just cosine, comes from cosine. And cosecant is a little bit difficult. It's ln cosecant plus cotangent with absolute value. So that's this term. So a particular solution now becomes negative y1 cosine x, or integrate this, just sine. Now sine times this one times this one. Simplify, in the end we get this. So this is a particular solution for that. Anyone has any question?
Quick question. For the final, we should know how to integrate cosecant, right? Like we should memorize
No,
that? Okay.
not to worry. No.
So the simple like sine, cosine, that stuff is okay. We don't need to.
Yes.
Okay.
Yeah.
Thank you.
Yeah. And any other questions? And that's it. That's all I want to talk about today. And next class, let's see, because some of you are able to study ahead of time. So next class, we'll be talking about electrical circuits. Let's see. Applications. Just some example of applications. You know what? I may want to skip that. Hold on one second. Let me check 12. Oh, no, this is a 12. I mean 13. Oh, back to elementary power series solutions. Okay, 14 is more interesting. Anyway, all right, anyone has any questions? So next class we'll be talking about electrical circuits. This is day 12. Okay, we're on schedule. All right, if you have no questions, I am done. Let me